This is our CS2316 final project phase 3, Nicholas Hoyt and Stephanie Son.
So our point of interest was that we wanted to focus on US electric vehicle readiness because EV adoption is becoming a major national trend, and we wanted to really focus on a topic that is relevant today and also in the future due to the sustainability and environmental concerns. And our goal was to understand how EV incentives, charging infrastructure, and EV demand patterns correlate with each other across states.
Yeah, so for our data collection, we collected the CSV when we were looking for just general data on electric vehicle consumption in different parts of the states. HTML was found when we were searching for states that had better electric vehicle readiness with EV charging stations. And the JSON was found when we were looking for different types of EV charging infrastructure in different places, and all of them had inconsistencies that needed to be fixed in our data collection, data cleaning.
So for our CSV data cleaning, we first used pandas to access the file, and then there were a lot of majority empty columns and rows, so we used dot drop NA with a threshold length times 55 to delete or to drop columns and rows that were more than 55% empty. And then there were also duplicate column names that refer to different data, so we used a for loop to differentiate the first and second occurrences. And then using those differentiated columns, we renamed them based on what the data was, so underscore weight and underscore percent. And then we restricted the data to just 1900 to 2100 for the years. And then we converted percentages to floats. And then the previous for loop did not capture the column 1990 to 99 since there was a dash 99. So for this loop, we did the same loop. And then we cleaned all of the text-based columns as well as rounded all the floats. And then we outputted it to clean county data.csv. Now for HTML, we use Beautiful Soup to parse through the Wikipedia pages, and we converted the first table on EV incentives to a data frame. We cleaned the text and renamed the columns, and then converted incentive amounts to clean numeric values. Next, we standardized the vehicle type column and converted carpool access to Boolean and filled in NA values with false just to make it easier to analyze in the future. And then we included only necessary columns in a copy and renamed the columns to finally export it into cleaned underscore EV incentives.csv.
And then for our third data cleaning, we used JSON to access the API's data. And then we cleaned the data by keeping only columns that were more than 50% filled so we didn't have a bunch of empty rows. And then we loop through to replace any NA values with n slash a or 0 if they were not an object. We then use pandas to better format our output so we could take care of a lot of the consistency inconsistencies, such as for Tesla, if the stir contained Tesla, it would be an is Tesla, and that goes for similar things for the rest. Then we created final columns that we wanted to include and return the last data frame. For Insight 1, we use sklearn components by importing those. And then we had to clean a little bit because it was erroring with some of the NaN values. And then we created has cache incentive column, which is what we wanted to predict based on our X data. And Y is what we're predicting. X is the model we used to predict. And then we pre-process the data by using a one-hot encoder for vehicle type so that we could get it all set up for our logistic regression. And then we use standard scaler for the incentive amount column so that it would be cleaner. The data would be cleaner with the numerical value. And then pipeline ran the logistic regression model with our pre-processed data, and we split it. And then we ran the predictions and recorded a perfect accuracy test. And yeah, the model was able to distinguish states that provided incentives from those that didn't. Then in Site 2, using county data file, we wanted to accurately predict future years' fuel share by county. We started by selecting the data types, and then we had to clean a little bit so that NA values were filled with 0 or unknown, depending on the situation. And then we set the Y variable to 2009 so that we would be using the generated model to predict 2009 fuel share. And then we set X to take into account all numeric and categorical columns to create a prediction model. And then we pre-process our data again. And then we use the pipeline to run the linear regression model and then split it. We achieved an R squared value of 0.966, which proves that the model could explain almost all of the variation. And our mean absolute error was basically zero, so the model was perfect, almost.
For Insight 3, we used the incentives in fuel station CSV to look at how strongly state and EV incentive amounts relate to the charging station infrastructure. And so first, since there was a mismatch between names and abbreviations, we manually mapped it. And then we found the mean, median, and number of incentives by state, as well as the ratio of private and Tesla stations. Then merging them together, we found the correlation between the average incentives and each charging station ratio, and then created infrastructure score to analyze the quality of charging stations. From this, we found that incentive size has almost no correlation with total station count and is mildly negatively correlated with Tesla network and private access ratio. In Site 4, we use county and fuel station CSV to analyze whether the availability of public charging stations in each state aligned with actual EV demand. So we took the most recent column to find the EV demand and then grouped it by state. We also calculated the stations per county. Then we normalized both demand by state and stations to find the infrastructure gap metric and the correlation between them. And the analysis showed that several states have substantial infrastructure gaps, meaning their EV ownership levels are not matched by sufficient charging availability. And finally, in Site 5, we use the county and incentive CSV to examine whether state-level EV growth is meaningfully influenced by EV incentive amounts. So doing the same mapping, and then we use the first and last columns of EV demand to find the average rate of change. And we found the correlation between the average incentive amount and the average rate of change. And then we found there was a slightly negative correlation, meaning states that offer higher rebates does not necessarily experience stronger EV growth. So financial incentives matter, but are not dominant drivers of EV adoption.
And then for visualization one, we created a pie chart to show the distribution of incentive types so that we could see which one EV friendly states would most likely use. And then for visualization two, we use the county data as CSV to show the consumption of gas by state in the year 2000, because the more gas heavy states would probably include more incentives to switch to electric cars in the future.
And then for visualization 3, we use the fuel stations to examine whether states with high Tesla network presence also provide publicly accessible charging infrastructure. And we found using np.polyfit, we found the line of best fit, and this indicated that states with high Tesla dominance tend to have lower public access percentages, suggesting Tesla heavy states may rely more on restricted or semi-private charging networks. And then the main challenges we faced was accessing the JSON file, especially with the API key, and then accessing and cleaning the CSV in Google Colab especially. And then results, we found that EV incentives show almost no correlation with EV growth, and that states show mismatches between their incentives, charging infrastructure, and actual demand, and Tesla heavy states tend to have more restricted charging environments. And overall, this concludes that no single policy lever is sufficient and financial incentives are limited in impact. So infrastructure must scale with demand, including charging and equity.
Thank you for watching.